Good afternoon, this is Schweitzer, and a little short video on really the bulk of our notes on what we consider position, time, how long it takes an object to move down a position. Keep in mind that when we're talking about a position, um, we're only in this point referring to something that would be linear, which means we're going really every scenario we're thinking about is a straight line, um, up and down a straight line. We're not moving in two dimensions, so keep that in mind. So the first term we have here is a scalar versus a vector. Okay, so a scalar versus vector. A vector is well, a scalar is something that just has what we refer to as a magnitude. Um, an example of a scalar might be temperature. And it really just has a number. It is, 90 degrees outside. That's it. Okay, a vector is something that has both a magnitude and a direction. So for that, a good example of this would be velocity. So speed is literally going like 50, mph, miles per hour, where velocity would do more than that. It would be 50 miles per hour east. Okay, so this is north, this is east, this is west, and this is south. So if you're traveling east at 50 miles per hour and you turn and go 50 miles an hour north, then you've changed your velocity. You're going 50 miles per hour. You're going 50 miles per hour. You haven't changed your speed, but you've changed your velocity. Okay. So a vector is often described by an arrow. Now you notice that my arrows are about the same length. So the length of the arrow is often reflective or proportional to the size of the vector. So this might be 50 miles per hour, but this might be 100. We'll use vectors a lot. So there are lots of vectors in physics. All right, vectors versus scalars. Okay, every time we do something like this, it's always a possibility that you're going to be wanting to stop, pause the video, and do it yourself. Okay, so most of the quantities used to describe motion can be categorized in either vectors or scalars. Okay, so categorize these guys out. Okay, you may be familiar with some, you may not be. So let's just kind of grab the speed. We know is a scalar. So velocity would be a vector. Okay. All right. Acceleration. You may not know this, but it is definitely a vector. Sometimes a vector can be as easy as just being a positive or a negative. So positive velocity typically means you're going to the right, and negative velocity means you're going to the left. So acceleration also has a positive or negative acceleration. We'll see that coming up. Okay. So distance versus displacement. Okay. Now this is always one that kind of confuses me. So a distance is just, and then displacement would they're related in the sense that the displacement is the net distance. Okay. So if you were to go down to your house, okay, and you went down to your friend's house, okay, and you came back home, what's your displacement? Your displacement's 0. What's the distance you've traveled? Okay, so you traveled a lot of distance, okay, but the displacement is nothing. If you just went from your house down to your friend's house, okay, and then you traveled back to the middle, okay, your displacement might be, let's say, 3, so your displacement, so you went down to here and you came back to here. So you went a distance x, a distance x, and a distance x. So your distance at that point you traveled, distance would be 3x. But your displacement is x, okay? And it could be positive x. So the displacement is the vector. Notice that in the distance, we didn't care if you're positive x, negative x. So I spent 2x going to the right, and I did x going to the left. Did the scalar care that one was positive and one's negative? Positive means it's going to the right, all right? Negative means it's going to the left. The scalar didn't care because it doesn't have that positive and negative. Just distance, marker slowing down, and displacement goes here. Okay, it's minor semantics. A quantity that is ignorant of direction. Okay, be scalar. Conscious of direction, vector. Okay, next one. How do we assign a direction? Okay, so what happens if we move it in one dimension? Okay, so again, we can actually assign these at any time we want on problems. Okay, there are some standards, stuff that we do, that we assume, but you could change it. Okay, but to the right typically is positive. To the left is negative. North typically is positive. To the right, east is positive. South, negative. West, negative. So even if I just say, for example, a student drives to Hortonville and 50 miles per hour, what's velocity? Okay, so we have to assign what we call a frame of reference, and this is super important. So frame of reference. Okay, so that's what we set up before the problem starts. Which way is positive, which is negative. So drives east at Hortonville. From Hortonville at 50 miles per hour. So east is positive. So what's the student's velocity? It's 50. Even though they don't say it, there's a positive on here, which means I'm going, at this current frame of reference, means I'm going to the right. Okay, so keep that in mind. So anytime, we'll use lots of velocities, and they're not going to always even have a number assigned up front. 20 meters per second. Okay, that'd be meters per second. And if they say 20, just because that positive is not on there, it is still there. Okay, it is a vector. All right, so here we go. How do we assign a vector? All right, so again, to the right it's positive, to the left it's negative. Up is typically positive, down is negative. So examples of some of these vectors, we have 50 meters per second, positive 50 meters per second, 50, they're all, you could say positive 50 meters west, okay? Again, that would be to the left. We could say negative. It could also be positive. I mean, just depends how you set your frame of reference up. Negative 50 meters per second, negative 50 meters west, 50 feet west. So here, negative 50 feet, that's a position. That's still giving me a distance traveled and a direction. That's a vector. Meters per second, west. This guy, because it's got the negative on here, is a vector. Okay. So lots of ways we assign our vectors. All right, distance, displacement. We've already talked about this. It's pretty easy to understand displacement. This is the net distance. Okay, so this is the net distance. This is the, I should say that, let's see, erase that. The displacement is the total, okay, total traveled. Back up again. Screw that up. Okay, so now I get these two mixed up. But so the displacement is the net distance, distance traveled. All right, how much you're displaced. Distance is actually how much you went. Okay, so is the um, total traveled. And occasionally you come across little terms that always tend to screw you up, but you know, just deal with it. So here it says, suppose that you run along 3 different paths from location A to B. On which path would your distance traveled be different than your displacement? Okay. Well, there's only one of them here where they're the same. Distance traveled and net distance is this guy, from here to here. That's the one they're the same. So this one's different and this one's different. Your net displacement is the same for every one of them. Okay. That's important. All right, so what is velocity? Okay, so our first section here really is a non-mathematical section. But we always want to keep in mind some of the formulas that we're working with here. So velocity is, so your distance, all right, or it could be your displacement, okay, but we're going to go change in distance, all right, is your distance, your change in distance divided by your change in time. Okay, what do you think is the difference between average and instantaneous? Okay, so this is just something that we're kind of looking at here. So an average would be different than instantaneous. Okay, if you're, the difference here is that if you're driving your car down the highway, okay, and you're down a line, and all of a sudden a cop down the way here hits you with a radar gun, all right, and they hits you, they're getting your instantaneous speed at that point. But from here to here, you may have had multiple different instantaneous velocities. So mathematically, instantaneous is when your time is very small. It's a very short distance with a very small time. I shouldn't say the distance has to be short, but the time frame is very small, so likely the distance may be small too. But so it's instantaneous, and it really is difficult to do instantaneous time for us um, uh, because we want to get this time microscopic. Okay? You run from your house to a friend's house that is 3 miles away. Then you walk home. Okay, so you ran here and then you walked back. What distance did you travel? Again, everything we do here should be paused and attempted on your own. But so, with that being said, what's your distance? 6. What's your displacement? 0. Okay. All right. Go ahead and give this problem a try. Observe the diagram below. A person starts at A, all right, walks along a bold path and finishes at B. Each square is 1 kilometer along its edge. Use the diagram and answer the next 2 questions. All right, so now this is not in just one direction, but we're always thinking of it in one direction. So we're going this way, this way. We always just kind of could break these sticks up and just line them up. Okay. So what the person walks a distance of? Okay, so each square is 1 kilometer, so we got to count them out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. The person walks a distance of 32 kilometers. What's the person's displacement? What do you think? All right, so displacement is just from here to here. So that's 1, 2, 3. And you notice how displacement also has a direction. This is an example of a scalar at this point. We didn't care which direction we went. The displacement would be 3 kilometers, but it's not just 3 kilometers. It's 3 kilometers east. And where's that one? Let's see here. There we go. 3 kilometers east. It went east. There's my legend. Or you might call that my frame of reference. Okay. All right. A cross-country skier moves from location A to location B, location C, and location D. So they went from, let's figure out, we went from A to B in 1 minute, and then each leg took 1 minute. So they went from A to B, and then of course B to C, and C to D. Okay, so let's answer the questions. What's the distance traveled by the skier during 3 minutes? Okay, so we went from 0 to 160. So 160 plus, and then each of these guys are 10. So went to C, 10, 20, 30, 40, 50, 60. I can just subtract 40 from 160. That's 120. Okay, and then back to, well, so A, first 3 minutes. So 1 minute, 2 minutes, 3 minutes. We want to do a third minute. And then from 40 to 120, we can subtract those two numbers and we're going to get what, 80? Okay. And I'll let you guys add those up. Okay. So what's the net displacement during the first 3 minutes? Well, they started here, they ended here, so 120. Okay. What's the displacement during the second minute? Okay. So first minute is 160, second minute is this. Okay. So displacement's a vector. So it's going to be 60 minus 40 was the 120. So it's minus 120. Okay. Or 120 west. What's the displacement in the third minute? 40 to 120. Subtract those two is 80. So it'd be a positive 80. Or it could be 80 east. Okay. All right. All right. So let's see what we got here. So we're looking at the idea of instantaneous speed versus average speed. Okay. In fact, we'll stop our little discussion here, give you a break, come back, and we'll discuss our next topic of instantaneous speed versus average speed.